Antibiotic resistance is an increasing threat to society. Large numbers of bacteria exist all around us. Because of random natural mutations, some of them are resistant to antibiotics. When exposed to antibiotics, the susceptible bacteria die. The bugs who are naturally resistant survive. The remaining resistant bacteria now have room to thrive and multiply. Resistant bacteria can transfer parts of their DNA that code for this resistance to other bacteria. Campaigns have been developed to limit unnecessary usage of antibiotics with the goal of preserving their effectiveness, but they are still heavily used. The antibiotic I work with is called ciprofloxacin. It is commonly used to treat a wide range of ailments, including urinary tract infections. My goal is to examine how Shigella, a common anaerobic bacterium, changes in response to increasing antibiotic gradients. I hypothesize that Shigella will be able to develop resistance to increasing antibiotic concentrations within 24-hour incubation periods. Since Shigella is an anaerobic bacterium, the initial 18-day experiment was conducted in oxygen-coated vials and transferred via needle syringes. In this experiment, 10% of the bacteria were transferred every 24 hours to a new vial with a higher antibiotic concentration. A vials were incremented by 0.2 MIC and B vials by 0.4 MIC each day to see if different increments affected growth, ending in a final concentration of 3.2 MIC and 7.4 MIC on day 18. This graph that displays optical density as a proxy for cell growth versus time shows how vials A and B compared to the control, which received no antibiotic over the 18-day period. As you can see, both A and B vials grew similarly, showing that different increment rates did little to affect growth. Their growth every day shows that resistance was developed within 24-hour incubation periods. To further understand the MIC threshold, I conducted experiments in an anaerobic chamber. This allowed me to work without needles and closed vials. Before entering the main chamber, everything must go through an intermediate container that vacuums the gas out and purges it with nitrogen. This device monitors the oxygen and hydrogen content of the chamber to make sure we are maintaining anaerobic conditions. Within the chamber, I set up 96-volt plates containing increasing MIC values in each row. This is done to try and find thresholds for growth of our cells gathered in the 18-day experiment. If you can recall, on day 18, the maximum concentration that B vials were grown to was 7.4 MIC. The results from the 96-well experiments show little to no growth for the control and growth all the way up to 90 MIC after 24 hours for vial B cells. This is worrisome because it shows that low doses of ciprofloxacin can lead to extremely high resistance within relatively short time spans. In future experiments, I plan to get the DNA of the cells from the 18-day experiment sequenced in order to determine where the genome is mutating and to hopefully give further insight to how it mutates. With this knowledge, we can get closer to understanding how to prevent the development of antibiotic resistance. In the meantime, it's best to try and limit society's usage of antibiotics to preserve their effectiveness for generations to come.